Alright, let's make sure that we have the correct pictures for all these. Okay. Hopefully we all got x squared, right? Okay, if I plot these coordinate points, let's see, it'll look something like this, right? So we end up with quadratic. Should be a little smoother down there. There we go. Okay, something like that. Okay. We jump down to the next row, a cubic function. At a cubic function, we will end up with something like this, and this is 2/6. This actually goes off the graph a little bit, right? So our cubic function does something like this. Our absolute value function, right? If I start plugging in values, we end up with a b. This is what the absolute value of x looks like. The square root function, we cannot plug in negative values, right? So we actually should just start at 0, and we end up with something that looks like this. Right. Our cube root function, down here, cube root is actually just a sideways cubic function. Okay, if I start taking the cube root of numbers, we end up with something that does this, right? Oops. Oh, no, that's right, yeah. Okay, we end up with something that does this. The reciprocal function, okay, 1 over x. This one, if we start plugging in a couple of values, we get something that looks like this. And if we plug in 0, we get something that's undefined. Right? That tells us there will be an asymptote at 0. So what ends up happening is something like this. Okay, we get our reciprocal function, 1 over x, to look like this. Then if I do 1 over x squared, similar idea. Okay, if I start plugging in values, the only difference is this piece ends up getting flipped up. Okay, that piece will be positive, but we'll still have an asymptote at 0. Okay, this graph just looks like this. Okay. So we're not going to do a whole lot more practice with these parent functions. Okay, this is just something that you are going to need to know and be able to recognize going forward. Right? On the next test, we may do some type of matching thing, right? Like match the x squared to the correct graph, that type of thing. Okay. But the reason we did this in this section, okay, so that we can easily graph piecewise functions. Okay, so on the back, we have a few examples of piecewise functions. Okay? Piecewise functions are just graphs or functions that are defined by multiple pieces. So in this first example, if I want to graph this, okay, I've got 2 different pieces. It says this function is the absolute value of x when x is less than 0, but it's x squared if x is greater than or equal to 0. Okay? So let's break this down piece by piece. Okay, first, I just want to graph the absolute value of x. Okay, we just did that on the front. So I'm just going to graph that whole thing, right? The absolute value of x, and I'm going to be careful to graph it in the exact right spots. Okay, I'm not just going to sketch a V real quick. I'm going to carefully sketch this into the right coordinate points. Okay, so, but now, if I look at this next piece of information, this says I only want the absolute value of x if x is less than 0. So I only want this graph for x is less than 0. Okay, so that's all the x's over here. So what I'm going to do is erase everything where x is not less than 0. Alright, so I'm just taking the absolute value of x. Okay, so I drew that whole graph. Okay, and once you get the hang of it, okay, you may be able to not draw the whole graph. But I think to start, it's a good idea if we just draw this whole thing and then say, well, I only want that graph where x is less than 0. Okay, now it's less than, not less than or equal to. So technically, we would have an open dot at 0. Right? Now, if I look at the next piece, I want to graph x squared. Right? So again, I'm going to ignore the domain part of this. I'm just going to graph all of x squared first. Okay, so that does something. Oh, so close. Alright, so x squared over here, x squared. Okay, so there's my whole piece of x squared. But if I then look at my domain, okay, this says I only want x squared when x is greater than or equal to 0. So I want to get rid of this part where x is less than 0. And so I'm going to erase all that. Okay, and I just end up with this piece right here. Now, what do I do with 0 on this graph? Is that going to end up being an open or a closed dot right there? It's going to be closed, right? Because this graph meets up at that point. Okay, and this graph includes 0. So in this case, in this piecewise example, we have a continuous function. Right? These two pieces end up meeting up at the point in question, at 0. Okay, so this would be our graph of this piecewise function. Right? The absolute value of x for everything less than 0, and x squared for everything greater than or equal to 0. You okay with that one? Alright, why don't you guys take a couple of minutes and try this second one here. Okay, graph x squared if x is less than or equal to 1, and then x plus 1 if x is greater than 1. Yes, but it's going to be a continuous line, right? Not just
Right. No, I want so I would say this is
x plus 1, so it's a slope of 1 and 1 intercept of 1.
So it's basically
this one ends up not connected. So the first part, x squared less than or equal to 1, so I'm just going to erase everything to there, right? But now if I graph this line, it's got a y-intercept of 1, and a slope of 1, so it's going to be something like this.
There will be one above.
Right. Right, so
I realized just did less good about myself. You literally sit and fully I felt considered that you're the business mobile. No. Actually, I don't. That's true.
So if I graph the line x plus 1, right, this is a slope of 1 and a y-intercept of 1. So I'm going to start at my y-intercept of 1, and then just...
Just say you're stupid ass. We know that. We know that. So who is your stupid ass?
Alright, for this second one here, I think we should wind up with something that looks like this. Why not? Okay, so let's do the whole thing. Let's go piece by piece. Okay. Again, I think it's until we like really get comfortable with this, it's going to be a good idea to just graph the whole thing and then look at the domain restriction. Okay, so for this first one, I just want to graph x squared. Right, so I'm graphing my x squared function. But now I'm going to look at the domain restriction. Okay, I just want that if x is less than or equal to 1. So here's x is 1. I don't want anything greater than 1. So I'm going to erase all the way up to there. Now that 1 is included there, right? So that endpoint should be a solid dot on this piece right here. Right? Well, for the next one, I want to graph the line x plus 1. Okay, so I'm ignoring the domain restriction. I'm just going to graph this line. Right? So this tells me a slope of 1 and a y-intercept of 1. Right? So I'm going to start at my y-intercept and then start just going up 1 over 1, up 1 over 1. Right? And we get a line that does something like this. Right? I'm just going to sketch this half of it because I know I'm going to end up erasing a bunch down here. So now we just want this piece where x is greater than 1. So I want to erase everything up until 1. Right? Well, that point is not going to be included in my red portion because x is just greater than 1. Right? So that will be an open dot on that piece. Right? So I think the best process here is just graph the whole thing and then look at the domain restriction. Right? Look at what piece you want to get rid of. Do the same thing for the next piece. Right? Graph that whole function and then get rid of the part you want to get rid of. Right? Especially for things like a line. Right? It might be, if you just try to graph that piece of it, it might be confusing. You might think, well, I need to start at 1. You're starting at 1 on the y-axis. So I think it's just graph the whole thing and then get rid of the piece you want to get rid of. You okay with that? All right. I'm actually going to, before we go to the greatest integer function, we're going to do another thing here. So if I give you a graph of a function, we want to write the piecewise equivalent of that. So let's say we've got something that looks like, let's see, how about, how about this is -2, -2, 0, 0. All right, how about something like this? Okay, we're given this graph, and from this graph, I want to write the piecewise function. Something to do with x.
You're on to something.
With the which one? So let's go piece by piece, right? So we want to figure out the function for all 3 pieces, right? So I'm going to end up with something that looks like this, right? Where I've got three pieces. F of x equals this. So the first piece, what is this function? Just x. How did we get that? So the y-intercept's at 0. So I know if I'm thinking y equals mx plus b, my b is 0. What else? It goes like this. Why isn't it 2x or 1/2 x?
It's -2.
So you found that the slope is 1, right? Okay. So if I'm going from -2 to 0, 0, I'd be going up to right 2. Okay. A slope of 2 over 2 is just a slope of 1. So the equation of this line would just be y equals x. So this first portion is just going to be x. What's the domain on that piece? That piece is defined for what x values?
Less than or equal to 0.
X is less than or equal to 0, right? Because we have a solid dot there. So x is less than or equal to 0. What's my next piece? What's the equation of this? C, yeah, so on the other side, we said, for any constant value. But in this case, we know that constant value. 3, yeah. So the equation of this line is just y equals 3, right? Or f of x equals 3. So, that's my middle piece here. What is the domain of that piece? What x values is that defined for? Greater than 0 and less than 3. Okay, so something like that. Okay, and again, neither of these points are included, right? So these are just less than symbols, not less than or equal to. All right, so those first two pieces were hopefully fairly straightforward. What about this last piece? I can't just see the y-intercept on this graph, or this piece. So how am I going to write the equation of this line, of this piece of the graph? Yeah, right, well, we did a couple of sections ago. Okay, we're going to have to go through the process of writing the equation of this line. So we have 2 points on the line, right? I can find the slope between them, and then use point slope to write the equation of that line. Right? So my slope formula, y2 minus y1 over x2 minus x1. Right? So 5 minus 2 over 3 minus 7. Slope of -3/4. So what do I do now? How do I actually write the equation of this line?
Yeah. Y minus, you can just use the 3, 5. So y minus 5 equals 3/4 x minus 3.
Right. So I'll go ahead and write out the actual equation and plug in values, right? Y minus y1 equals m times x minus x1. That was our point slope form of a line. So yeah, we can choose either of these points, but if we choose the 3, 5, 5 would be my y value. We just found the slope to be -3/4 times x minus my x value. So I'll go ahead and distribute this 3/4, so -3/4 x plus 9/4. Then if I add this 5 over, -3/4 x, it's 9/4 plus 5, 29/4. Thought about it. We okay with that process? Right, we did this a couple sections ago. It's going to creep back up again now. So now, this is my third piece of this piecewise function. Right? -3/4 x plus 29/4. Where does that define? x is greater than or equal to 3. Questions? All right, so with piecewise functions, we're going to do both of these things, right? We're going to say, here's the function, graph it, and here's the graph, give me the function. Okay? So the last thing here, okay, is just graphing the greatest integer function. Does anybody know how the greatest integer function is defined? The greatest integer of x is defined as... Nope. So this is something that's not super common, right? This is probably the only section we're going to look at this. Greatest integer of x is defined as the greatest integer less than or equal to x. Alright. So our notation. In the book, it's got a double bar like this. Okay. More commonly though, when we write it, we call this a floor function. Okay, so we write it like that. Okay, in the book, it's going to show up like this, okay, with these like double bracket things. All this is basically rounding down. Okay, if a number isn't an integer. So, for example, okay, if I want the greatest integer of 5, right, well, that's just going to be 5. Okay, if we already have an integer, the greatest integer of an integer is the integer. 2.8. Okay, if I'm rounding down to the greatest integer less than or equal to 2.8, 2. If I'm rounding down 7.2 to the greatest integer less than or equal to 7.2, 7, right? If I'm rounding down negative 4.2 to the greatest integer less than or equal to negative 4.2, what am I going to get? What is it? Is it negative 5 or negative 4? Which one is it? Negative 5. Right? Negative 4 is greater than negative 4.2. Right? We want the greatest integer less than or equal to x. So the greatest integer less than or equal to negative 4.2 is negative 5. Okay? So let's graph this real quick. Okay? Let's see what the graph of its step function would look like. Okay? We're not going to look it up in the book. We're going to see if we can figure this out ourselves. Alright? So let's just start in the positive. Let's just look at quadrant 1 first and then see if we can expand this to the whole graph. So if I'm looking at, let's go to 5. If I'm looking at 1, if I plug 1 in to this greatest integer function, what am I going to get? 1. If I plug 2 in, what am I going to get? 2. Right? If I plug 3 in, 3. If I plug 4 in, I get 4. Right? And so on. Okay, so if I'm just graphing each integer, it kind of looks like it's going to be a line. But let's see what happens in between now. What if I guess we can do 0, 0 as well, right? So what if I plug 1/2 in? What do I get? 0. What about 3/4? 0. Right? So what ends up happening, okay, from 0 all the way up to 1, it's going to be a horizontal piece. But at 1, I jump up, right? So at the end of this, we're going to have an opened up. Right? Similarly, if I plug in 1.5, I'm just going to get 1. If I plug in 1 3/4, I'm going to get 1. Right? So we end up getting a horizontal line here. But then at the end, at 2, we jump up. This process is going to continue. Right? I'm going to get a horizontal piece at each one of these that ends with an opened up. Okay? This is called the step function. Right? This process would continue if I go into the negatives. Right? Greatest integer function looks something like this, okay? And the key to remembering this is just our definition of greatest integer. Greatest integer is just the greatest integer less than or equal to x. Okay, again, the notation in the book, it's this double bracket thing, but usually we just write it, or call it the floor function. I guess we jot that down, okay? This is also called the floor function. Questions? Into this function. So plugging it in just means using our definition. So our definition is the greatest integer less than or equal to that, right? So if I say 1.5, I plug that into this function, that gets me out 1. Other questions?